Hi there, Mr. Sutton here, bringing you the AB Calculus 613 Extra Practice Number 5 solutions on volume of solids of revolution. For this problem, they're telling us R is the region in the first quadrant bounded by the graph of 2 tan of x over 5, 5 minus x, and the y-axis. They want the volume of the solid generated by revolving this region around the line y equals 6. This is a grapher question, so let's start by graphing all this out and seeing what we're looking at. So here I am in the y equals. I've put, let's see, this first one in, I'll put my tan function in the y1, my line I put in y2, and this is my axis of revolution, y equals 6. Not really sure exactly where to go with the window, so let me just do zoom 6. And we've got a whole bunch of craziness all over the screen here. There's my tan function, there's my line, and there's my axis of revolution. And while I'm at it, let me define the tan function as f of x, and I'll let g of x be my line, just so I can refer to them quickly. All right, so there's my picture. Now, I need to figure out, first off, what region am I dealing with here? Well, I need the region between these two curves and also the y-axis. So that's this region right here, this little kind of, it's not quite a triangle, it's more like, I guess, a wedge of pi or something. But I'm revolving this around the line y equals 6 up here. So one thing I need is my limits of integration. So I'm going from left to right. And on the left side, I've got the y-axis, which is the x value 0. On the right side, I have whatever x value this is, which I don't really know yet. So let me figure out where these functions equal each other, and that'll give me that intersection point. So to find that, let me do second trace, option 5, intersect. And let's see here, move my spider along this curve, press enter. Second curve, let me just make sure I'm on the right curve here. Yep, that's the one I want. Press enter, and then press enter a third time. Come up with about 3.3896, which I'm just going to refer to as P herever after. And I'm also going to store it on my calculator. Let me quit out of there, and let me save that value. So I'll store that as alpha p. There we go. Now I'm not worried about losing it. All right, so the area that I need to revolve now, or at least the area I need to integrate on the interval from 0 to p, is going to be a washer, because I have this gap here between this bounded region and the axis of revolution, so I need a donut as my, my model for what I'm slicing and adding up. So I'm going to have a of x equals pi times big R squared minus little r squared. Big R squared, that's the distance between the axis of revolution and the further away part of the bounded region. So that's going to be 6 minus that tan function, so 6 minus f of x, and we're squaring that. And then little r squared, that's going to be the distance from the axis of revolution to the closer function. So that's going to be 6 minus g of x, and squaring that as well. So now for the volume, I need to take the integral from 0 to a, or actually p in this case. I called my number p. And I'm going to just do a of x dx for what I'm integrating over that. And now it's time for the calculator again. Just to make this as tidy as possible, I'm going to define my a of x function as a y equals. I'm going to put this in y4. So I'm going to have, let's see, pi and times, I've got to open a parentheses now, and open another parentheses. So in this parentheses, I'm going to put big R. So that's going to be 6 minus the f function. So that's 6 minus alpha trace y1. Close that parentheses and square it. Now I have to subtract another parentheses. This is little r. This is 6 minus the g function. So alpha trace y2 for that. Close that and square it. Close the big parentheses. All right, so that's my a of x function. Let me quit out of there now. And let me go to Math 9 for integral. I'm going from 0 to alpha p. And now I just have to put in alpha trace y4 for that a of x function. Dx. Press enter. About 209.617. So that gives me choice D. For this problem, I want the volume of the solid generated when the region between x cubed, the x-axis, and x equals 2 in the first quadrant is revolved around the x-axis. So if you just think about what's happening, we have x cubed, the x-axis, and x equals 2. So basically kind of a triangular-ish kind of shape being revolved around the x-axis. Since this shape is flush against the x-axis, we're just going to be using disks on this one. So we have pi r squared for the area formula that we're integrating. Our limits of integration, well, we'll get to that in a sec. Let's talk about the radius. So the radius is the distance between the axis of revolution and the outer boundary of the bounded region. So that's just from the x-axis to the highest function here, x cubed. So we're just doing pi times x cubed squared. And now I'm going to take the integral from, let's see, the origin to x equals 2. So from 0 to 2. I'm going to pull this pi out while I'm at it as well, because this is a constant, so I don't have to keep that inside the integral. So I'm going to have pi times the integral from 0 to 2 of, I'm going to simplify this to x to the 6th dx. Antiderivative, we're going to have, let's see, this bumps up to a 7, so we have 1 over 7 x to the 7th. Still have a pi kind of hanging around, evaluating all of this from 0 to 2. Now to make my life easier still, I'm just being really lazy here, I'm going to pull out this 1 over 7. So I'm going to have a pi over 7 out in front of everything. Inside I've got 2 to the 7th power minus 0 to the 7th power. I am going to have to simplify this, though. That's why I'm being kind of lazy here, because the answer choices are all simplified. So 0 to the 7th is gone. We've got 2 to the 7th times pi over 7. Well, 2 to the 7th, I don't know. 2 to the 6th, I know is 64. So 2 times that would be 128. So we then have 128 pi over 7, which is going to give us answer choice D. On this problem, which is a no calculator problem, they're telling us R is the region enclosed by the graph of y equals 5x minus x to the 4th and the horizontal line y equals 3/2. And we have some points of intersection, which we're calling x1 and x2, and x1 is smaller than x2. We want to know which expression gives our volume when we revolve this region around the line y equals 3/2. So this is kind of a tricky one, because usually we like to have a visual when we do these area volume problems, and here we're kind of flying blind. So in case you were wondering, no, you're not really expected to know what 5x minus x to the 4th looks like. It's some kind of polynomial. It's a negative 4th power polynomial, so we know it kind of looks like an upside down parabola in the long run, but in between the negative and positive infinity, we don't really know what's going on. We do know, however, that there's some bounded region that begins at x1 and ends at x2, because these are the 2 points of intersection, and there's really no other curves listed to bound the region. So we know that our limits of integration when we take an integral to do this thing are going to be x1 and x2. Doesn't help pick an answer choice, because that's what all the limits of integration are in the answer choices, but it's a start. Next thing we need to know is, are we using disks or washers? If we're talking about volume of revolution, it's going to be one of those two things. Well, the key here is recognizing that one of the boundaries, this y equals 3/2 line, this is also an axis of revolution. So if one of your whole boundaries is the axis of revolution, then that means you are flush, your bounded area is flush against the axis of revolution, which means you're going to use disks. So we can start with a of x equals pi r squared is kind of our starting point. And then the radius is just the distance between the other boundary and the axis of revolution. So that's going to be this function here, the difference between 5x minus x to the 4th and 3/2. So we'll plug that in just a sec. Now, one thing you might be wondering before you plug this in is, what order do I have to subtract these things in? I mean, without having the graph, it's kind of hard to tell which is the top and which is the bottom function. Just the way that this is laid out, I mean, for most of it, this polynomial is like an upside down parabola, so I'm guessing this is the higher function and this is the lower one. In the end, it doesn't actually matter, because whichever order you subtract them in, you're going to be squaring r, so it's going to come out positive no matter what. But if you look at the answer choices, it looks like the 5x minus x to the 4th is first in pretty much every setup, and the 3/2 is being subtracted. So we're going to go with that direction. So we then have pi times 5x minus x to the 4th minus 3/2. And all of that's being squared. So now plugging that in my integral, I can actually have a pi outside the integral. And I've got the integral from x1 to x2 of, well, all of this stuff with a dx after it. Now I just have to match that with one of my answer choices. And it looks like that's going to be answer choice C. A is pretty close, but they didn't have a pi outside, so we're going with C. For this problem, we have this S region that we're trying to revolve around the line y equals -1. And we just want the integral that does that for us. So let me see here. I need to find my limits of integration first, and they told us that these functions that are giving us this region were intersecting at x equals a and 0. So we have the integral from a to 0, and we have that in all the answer choices, so that doesn't really narrow anything down. I also need to figure out if I'm using disks or washers, because we're doing a volume of revolution, a solid of revolution here. Since I have this gap between the bounded region and the axis of revolution, that means I need washers. So a of x equals pi times big R squared minus little r squared. Big R is just the distance from this axis of revolution to the further away function. Since this one up here is negative x, big R is going to be negative x minus -1 or +1. So we'll be squaring that and putting that inside a big parentheses with a pi outside. Little r is the closer function minus the axis of revolution. So that's this crazy x squared ln function, +1. All of that being squared and subtracted. So now my integral, we're just going from a to 0 using a of x dx in there. Now matching one of the answer choices, this is a little bit tricky. We have a pi in a of x, it's part of a of x, so we can actually take that pi outside the integral, which means we need a pi somewhere anyway, so that eliminates choice B. You'll also notice here that both of these things have parentheses that are being squared. We don't have the individual parentheses being squared. Here in choice A, everything is being squared instead of big R and little r individually. So A is not quite correct. With C, these are pretty much the same except that we have -1 versus +1 inside big R and little r. And it's supposed to be +1 because you're subtracting -1 here. So that means we're going to have to go with choice D. For this problem, we have this R region enclosed by this crazy exponential function in the line y equals 2. And let's see here. We're told that these are intersecting at x1 and x2, and x1 is less than x2. We want the volume of the solid when we revolve R around the line y equals 2, which happens to be one of the boundaries of R. So because that's one of the boundaries, that means that our bounded region is flush against the axis of revolution, which means that we have to use disks instead of washers to integrate this thing. So I'm going to go with a of x equals pi r squared for my starting point. And the radius here, that's just going to be the distance from the axis of revolution to the other edge of the bounded region. So that's going to be this 10 e to the negative x sine of x function minus 2. So we're going to be squaring that and multiplying it by pi. Now my integral, we're just going to have from x1 to x2, and I'm also going to pull a pi outside of that. So we have pi times the integral from x1 to x2 of all of this stuff. So let me just put all of that in there. And let's see if that matches any answer choices. So we need a pi outside. That gets rid of a and b. And it looks like we need this whole thing to be squared instead of things being individually squared. So that means we have to choose C, not D. For this problem, we're told that R is the region in the first quadrant bounded by these two functions here and the y-axis. We want to know the volume that we generate when R is revolved around the line y equals 4. So let me start by labeling these. I'm going to call this 2 cosine of x over 3 f of x. And then this x over 4, I'm going to call that g of x, just so I can refer to them quickly as I'm explaining this. Let me go ahead and graph all this out along with my axis of revolution here on the calculator. So to graph all these, I'm going to go to my y equals. I'm putting the f function in y1, g goes in y2, and my axis of revolution, y equals 4, that's my y3. No idea what my window should be, so let me just do zoom 6 and hope for the best. So there's my cosine function. And next up is my line, the g function. And then there's my axis of revolution. So I could probably zoom in a little bit more. Let me just make my window. Let's see here. They said the y-axis is one of our bounding curves. So let me make my window. Let's just leave the window the way it is. We don't really need to zoom in too much more. One thing we do need to do, though, if we want to find, so it's this area right here, and we're revolving this around y equals 4. One thing we do need to do is figure out where the f and the g functions are intersecting, this spot right here. Our interval in general is going to be from 0 to whatever this spot is, but I need to find that. So let me go back to the calculator to do that. So let me do second trace, intersect, and then let me just go over to that spot with my spider, press enter again, and one more time. Gives me 3.3968, and I'm going to refer to that herever after as point P, or x value P. In fact, on my calculator, I'm going to actually quit out of the graph and store that x value I just got as alpha P. Don't want to lose it. I have a feeling I'm going to need this in an integral in a minute. So speaking of integrals, I'm going to be integrating some kind of area across the interval from 0 to P. What kind of area? Since I have this gap between my bounded region and my axis of revolution, that tells me I have to use washers rather than disks. So I'm going to write a of x equals pi times big R squared minus little r squared. Big R is just the distance from the axis of revolution down to the further away part of the bounded region. So that's going to be 4 minus this lower curve. This lower curve was just this line, g of x. So we have 4 minus g of x, the whole thing squared. Don't forget we still have a pi out there, by the way. And now I'm going to be subtracting little r squared. That's going to be 4 minus this closer curve, which we said was f of x. So 4 minus f of x squared, and that's being subtracted. So my integral then for my volume, I'm going to be doing 0 to p here of this a of x function I just came up with. And I'll put a dx in there just to make it official. Let me do this on the calculator now. So there's a lot of different ways to enter this. I'm just going to do this without making any new functions here. I'm just going to use what I have. So I've got a pi first of all. Let me put that down. I can take that pi outside the integral when I actually do this out. So I'm going to have pi times, now let me do my integral, math 9, integral from 0 to alpha p. And one of the reasons I took out the pi is so I don't have to mess around with yet another set of parentheses in there. I'm already going to have enough of it as it is. I'm going to have basically big R squared minus little r squared inside the actual integral here. So I need a squared parentheses for both of them. For big R squared, open a parentheses for that. Parentheses, there we go. I've got 4 minus the g function, which is going to be alpha trace y2. That's where I stored my g function. Close the parentheses and square that. Now I have to subtract little r squared, subtracting 4 minus f of x squared. So that's going to be, let's see here, open a parentheses, 4 minus. Now I have to do alpha trace y1. That's where I stored f. Close my parentheses, square it, and I should be all set in there. Let me put an x out here next to the d. Press enter, and we get 74.255, which matches answer choice D. On this problem, no calculator problem, we have this S region bounded by y equals x, that's the upper function here, and also x squared over 4. And they're just telling us that these intersect at 0 and 4. I mean, we could have found it on our own, but they're just saving us a little time. We want the volume when S is revolved around the line y equals -2, which let me draw that down here. There we go. All right. So I already know my limits of integration for the integral I'm going to have to set up here. It's just the 0 and 4 that form the edges of this bounded region. But I need to figure out which area formula I'm using for my cross sections. So am I going with disks or washers? Because it's always one of those for these solids of revolution. Since I have this gap between my bounded region and the axis of revolution, I'm going to have to use washers. So a of x equals pi times big R squared minus little r squared. Big R, that's the distance between my axis of revolution and the further away part of my bounded region. So from my axis of revolution to the upper function here, it turns out. So that's just going to be x, which is this function up here, minus -2. That'll give me that distance. So I can actually write that as x plus 2, and I have to square that now because it's big R squared. Still have that pi out there. Don't want to forget that. Now I have to subtract little r squared. So that's going to be this closer in function, x squared over 4, minus -2, so plus 2. And again, we're squaring all of that. So at this point, I have the integral from 0 to 4 of, well, a of x dx, but I actually have to match it with an answer choice carefully here. One thing that helps is we can pull a pi outside of the integral when we're actually doing this. So that eliminates choice B. You'll notice also that big R and little r are both being squared individually. So that gets rid of choice A, where everything is being squared like all at once. So we're down to C and D. Now the difference here is that we have minus versus plus 2. So that leads me to choose choice D then. For this problem, we want the volume of a solid that's generated when the region in the first quadrant bounded by x to the fourth, the x-axis, and x equals 1 is revolved around the x-axis. So for this one, just thinking about what the graph of x to the fourth looks like, it's basically a more severe version of a parabola. We're going through the origin, and we're going until we get to the line x equals 1. So our limits of integration for this volume are going to be 0 and 1. But we need to figure out, am I using disks or washers? Well, since this is between x to the fourth and the x-axis, and the x-axis is the axis of revolution, that means our bounded region is flush against the axis of revolution. There's no gaps. So that means we use disks instead of washers. So we can use pi r squared for our area setup. The radius is just the distance from the x-axis to the other bounding curve. So basically just x to the fourth. So we have pi times x to the fourth squared. All right, now I'm going to integrate that from 0 to 1, and I can pull this pi outside while I'm doing that, by the way. And I'll have inside, I'm going to simplify this to x to the 8th, but it is the same thing. Put a dx in there as well. So now using the reverse power rule, because I have to do this by hand, this is a no calculator problem, we have this bumping up to a 9, so we have 1/9 x to the 9th. Still have a pi outside. We're integrating from 0 to 1. I can pull this 1/9 out here as well to be with the pi. So I can write pi over 9, and now inside I'm going to have 1 to the 9th minus 0 to the 9th. So that's really just pi over 9 times 1, which is just pi over 9, giving us answer choice D. On this problem, no calculator problem, we have R, this region here, bounded by this crazy-looking function, the x-axis, and a vertical line. We want the volume of the solid generated when R is revolved around the x-axis. So we have the limits of integration for the integral we're about to set up. We've got 1 and 4, so that's pretty straightforward. We need to figure out, though, the area formula that we're integrating. Am I going with disks or washers? Since my bounded region is flush against the axis of revolution, the x-axis, in this case, that means I'm using disks. So we've got a of x equals pi r squared for this one. And the radius is just the distance between my axis of revolution and the other bounding curve here. So really just this y function up here. So there we go, that whole thing being squared. Now I am going to simplify this a little bit. I'm about to integrate this thing from 1 to 4, but I'm going to have to do this by hand, so this is going to be a huge nightmare if I don't clean it up a little bit. So let me start by squaring the numerator and denominator. That'll give me a 9 times an x minus 1 quantity squared upstairs. Downstairs I've just got x instead of radical x, so that's a little nicer. And I'm also going to go a little bit further here. I'm not going to do it completely, but let me simplify just a little bit more. I'm going to expand this x minus 1 squared. So that's going to be x squared minus 2x plus 1. Still leave a 9 out there. And at this point, it's time to integrate. So again, integrating from 1 to 4. Now when I do this, I'm going to pull a pi outside my integral. I'm actually going to pull out this 9 as well. So I'll pull a 9 pi out of there. I've got integral from 1 to 4. And inside now, I've basically got x squared minus 2x plus 1 all over x. I'm going to simplify that now by dividing each of these things by x. That's going to allow me to use my reverse power rule, which will make my life a whole lot easier. So I've got x squared over x, which is just x. Negative 2x over x is negative 2. And 1 over x, I can keep that as 1 over x, or write it as x to the negative 1, either way. Don't forget the dx there. Going from left to right now, I've still got my 9 pi out there, and this x, this is now going to be 1/2 x squared, minus, now we've got 2x, and antiderivative of 1 over x, that's going to be ln absolute value of x. Still evaluating from 1 to 4. So I've got a 9x outside, and I've got all of this stuff with 4 plugged into it, minus all of this stuff with 1 plugged into it. And if this is the real AP exam, then I'm stopping here. This is all constants. Even this ln stuff is considered a constant. So if you got all constants, you're done. If we wanted to simplify, though, then I guess we can keep going. So this first bracket, for example, this is half of 16, which is 8, minus another 8, so those actually cancel. All that's left from that first bracket is ln of 4. Over here we've got, let's see, this will be minus 1/2 plus 2, and ln of 1 is just 0. So minus 1/2 plus 2. If you really wanted to, I guess you could combine the minus 1/2 and the plus 2 to give us plus 3/2. And you could distribute the 9 pi, but I mean, at some point, you know, we've got to stop. So let's just call it a day on this one.